So this video, we're going to talk about the valence shell electron pair repulsion model, aka Vesper, right? So the Vesper theory, really, it's a theory, we use this to predict the molecular shape of the molecule, right? And it's the way this works is that we figure out how many electron charge clouds surround the atoms of question, right? And assuming that the clouds orient themselves far away from each other as possible, all right? So what do I mean by that? So like, for example, if you were to consider carbon dioxide, CO2, right? Now, if you go through the whole process of drawing the Lewis structure of carbon dioxide, which let's go ahead, let's just do that for the sake of this. So we know carbon has 4 electrons, oxygen has 6, and there's 2 valence electrons. So there's 12. We add this up. We have 16 valence electrons. Now, go ahead and pause it right now so that way it gives you some time to actually draw the Lewis structure of carbon dioxide and then unpause it to see if you're right. All right, so after that, we know that carbon's the central atom here. So I have carbon, okay, and I would connect it to make the structural formula of oxygen. Okay, so here it is. Now I'm gonna add my lone pairs to my oxygen. Okay, now I'm gonna add this up. So I have 2. Let me just go ahead and highlight it so you guys can see how I'm counting. So I have 2, 4, 6, 8, 10, 12, 14, 16. So here I see that I have 16 valence electrons. If I subtract the 2, I have 0. That means I got nothing more to give to my carbon. But I see my carbon doesn't have a full octet. So I'm going to take 2 from this oxygen. And I'm going to take 2 from this oxygen. So that way carbon could have a full octet. So at the end of the day, all right, carbon's going to look like this. Whoa, the oxygen's a little bit too close. Let me fix that. Let me draw my lines here. Okay, now, Vesper. What are we talking about, Vesper? So Vesper, we're looking at the electron clouds, or places where the electrons are. Now, the assumption is because electrons are negatively charged, they will repel each other. That's the whole idea of valence shell electron pair repulsion. All right, they will repel one another, and they're gonna do it in such a way. They repel in such a way that they're gonna be as far apart from each other as possible. All right, and so when you think about this, like if you're considering carbon here, so if carbon is our central atom here, right? That's what we're looking at, and we're thinking about all the electrons that's around carbon. Then we're considering these electron pairs. Okay. Now these electron pairs are going to naturally repel one another, all right, because they are opposite. They are not opposite charge. They are the same charge, so they are negative charge. So they're gonna repel each other, and they're gonna do it in such a way that they're as far apart from each other as possible. So knowing that, then we could predict the shape of the overall molecule. So in this scenario, we could rightfully assume that they're going to be, completely an opposite sides of carbon. All right. And so if I would kind of draw this out where you have the carbon here, and then so the electron pairs are going to be completely opposite sides from each other, to the point where it's as if it's at 180 degrees away from each other. All right. If you are looking at carbon as your focal point, right? So since it's 180 degrees away from each other, or these electron clouds are 180 degrees away from each other, then we could see that the molecular geometry of carbon dioxide, we would simply say that it's in a linear shape. All right. I know it's sounding kind of confusing, but we'll get through this. And so I'm going to kind of show you I will show you a little bit more from a really cool website called PhET. All right. And it's completely free, and I will drop the link as well. But then we get to see all this in a 3D, from a 3D perspective. Now, when you're looking at the CO2, what you notice is that you have 2 pairs of of electrons against this center atom here, right? And so when we're looking at the center atom, we only have we have these two pairs of electrons that's bonded to the center atom. Now there's different types of pairs of electrons. We have what we call bonding pair, right? Bonding pairs are obviously electrons that are bonding two different nuclei, like we see here. And then we have what we call lone pairs. All right, and these are pairs of electrons that are not bonded between or not bonding to pairs of nuclei. So example of those are like these right here, these oxygens. The electrons that's outside these oxygens. So these what we are considered lone pairs. But when we come to trying to determine the Vesper model, we always kind of look at the central atom, and we're looking at the bonding pairs versus the lone pairs. All right, and that helps us to determine what's the shape of the molecule. All right, and so like for example, let's say that we're talking about, so here's a good example, H2CO, okay? And so if you go through the Lewis structure and you draw the Lewis structure of this compound, right, and we go through the steps, which I'm not going to do this now, but because we're talking about Vespers, but you have a carbon here. We have two H's stemming from it, and then we have a double bonded oxygen. Okay. Now, if you're looking, you're trying to determine, okay, well, how many bonding pairs of electrons we have, and how many lone pairs of electrons that you have. This will kind of help you figure out what's the shape, what's the overall shape, right? And if you notice, well, we got 3 bonding pairs of electrons, and we got 0 lone pairs of electrons. Okay, and so knowing this, all molecules that typically have these set numbers of bonding pairs versus lone pairs, they pretty much have the same geometrical shape. Okay, and so the geometrical shape in this case is what we call Trigonal Planar. All right, and so here, if you could kind of envision this, it's basically like a flat triangle within a 3D space. These bonds are 120 degrees away from each other. That's the degree space they have away from each other. All right, and so this is typically when you have about 3 electron groups attached from the central atom. Okay. Well, there's another variation where you can have 3 electron groups attached to the central atom. It just looks a little bit different, and the shape is a little bit different. All right, and so an example I want to give of that is SO2. Okay, now SO2, what you'll notice is that not only that you have, in terms of bonding pairs, right, we have 2 bonding pairs, 1, 2, but from the central atom, all right, we have 1 bonding pair, 1 lone pair, I'm sorry, 1 lone pair of electrons. So here, we still have 3 electron groups around the central atom. All right, but it looks different. All right, but this time now we have 1 lone pair, so this is kind of a variation. All right, and so in this case, what's the bond angle? Well, if you notice, this lone pair of electrons has a lot more room to kind of flow because it's not restricted between 2 nuclei, right? So it has more room to flow, and because it has more room to run around, it actually creates a greater repulsion against these bonding pairs. Okay, now because it creates this greater repulsion against these bonding pairs, this bond angle between the bond pairs is actually less than 120 degrees. Okay, how much? It really depends on the molecule, right? So that's why I kind of want to create a general rule on this one, but it's less than 120 degrees in this case. So how to remember this? Well, think about this. Both of these consist of 3 electron groups. All right, that's the similarity between the two. All right, where the first one, because they're both 3 electron groups, when we think about the bond angles, all right, if you think about a triangle, well, I can't say triangle, never mind. But when you think about this, they all have bond angles of about 120 degrees. If it's no lone pairs, the bond angles is 120 degrees. If you have a lone pair, then the bond angle will be less than 120 degrees. So it's like a derivative of trigonal planar. Okay, this shape here, we say that is a bent shape. Why? If you think about the molecule in itself in a 3D space, and you can't see the electrons, right? The electrons are just too small. Then when you're looking at this molecule, it's like, oh, this molecule looks bent. Because it does. Because of these electrons, it looks bent. So we said the 3D shape of this molecule is simply bent. All right. So let's look at another geometrical set group. All right. And so let's imagine if we have four electron groups, right? So I'm going to say 4 electron groups here. So that way we could see the similarities between them. All right. And so let's say we have 4 bonding pairs. All right. So let's start with bonding pairs. And I'm writing my lone pairs here. So if we have 4 bonding pairs, so let's consider the molecule methane. Okay. It has 4 bonding pairs. It has 0 lone pairs. All right, so what is this? Its shape. All right, I'm gonna do my best to draw this as good as possible, as well as possible, that you can kind of see this from my drawing here. But as I said, I'm going to drop the FET link. You could try it out. Definitely in class we'll play with it so that you guys can see exactly what I'm referring to. But let's say you have, here's your central carbon here, right? And then so you can imagine that you have a hydrogen that's sticking straight up, okay? Kind of coming out towards you, you have a hydrogen, okay? And kind of behind here, you have another hydrogen, and off to the side here, you have another hydrogen. So this is the shape. This is me trying to draw this geometrically, right? This is the shape of methane, right? So methane, we'll say, in this case, if you notice, I have 4 bonding pairs. So here's my 4 bonding pairs. There's no lone pairs here. The geometry, or the bond angle really, of between one bonded hydrogen or one bond pair to another bond pair, we say that it is 109.5 degrees. Okay, and you kind of think about this, it's like, okay, there's 4 things coming off of it. Why can't we not have a square? Well, let's think about the square, right? It's a flat square. So if you have a square, actually, all right, here. So here's a square. So you can imagine, look, it's a shape of a square. But we know the bond angles between one bond to another in a square has to be 90 degrees. Well, 109.5 degrees is a further distance. The distance away from the bond angles are further apart at 109.5 degrees than at 90. Okay, so this is the reason why it doesn't take this geometrical shape. All right, because remember, electrons try to be away from each other as much as possible. Okay, so this is the reason why it picks up this shape. All right, and this shape, we call this shape tetrahedral. Okay, so we said the molecule is at a tetrahedral shape. Okay, now let's look at another derivative of this, where we have 4 electron groups, but we replace one of them with a lone pair. All right, so here's an example. We have NH3. Okay, what we see here is that we have 3 bonding pairs. So how many bonding pairs? We have 3, but then we have 1 lone pair. Okay, so how does this affect things? Remember what I said, this lone pair will actually push against the bonding pairs closer to one another because these electrons have a little bit more space, so more repulsive actions. All right, and so if I was to try to draw this geometrically correctly, and this is just me attempting, all right, so we could imagine you have a hydrogen down here. We have about another hydrogen here, another hydrogen here. So then we would say the bond angle between this bond and this bond, we would simply say that it is less than 109.5 degrees, because it really is. Okay, and it really kind of depends per molecule. I think in this case the bond angle is about like 107. All right, for ammonia in itself anyways. All right, so what is the shape of this molecule? Well, if you kind of pay attention, all right, we have this pyramid type of shape. All right, and so what we call this, we will simply say that the shape here is Trigonal Pyramidal. All right, because it kind of has this triangle base at the bottom. All right, and it's a pyramid. All right, so it's a trigonal pyramidal, because remember, in molecules, electrons are too small to see, and so what we will see is something that looks like a pyramid. Okay, well, what if we still have the 4 electron groups, but we replace one of them with another lone pair? All right, so we have 2 bonding pairs, but then we also have 2 lone pairs. All right, a famous molecule that looks like this is water, because it has 2 lone pairs. So here's our 2 lone pairs, and then here's our 2 bonding pairs. Okay, so how would that look like? Okay, well, now we have these repulsions by these electrons, and they're really repelling one another. I mean, you got 2 lone pairs, so it's going to be pushing against these bonded pairs pretty close to one another. I mean, you'll probably be more correct drawing it like this, right? And so when we're thinking about the bond angles here, I mean, for safe, because there's still four pairs, we'll still say it's less than 109.5. We know that for sure. I think for water's case, it's closer to like 104, 103 degrees, 103, 104 degrees. But so generally speaking, all molecules that typically have these 2 bonding pairs and 2 lone pairs, I mean, you could rightly say, yeah, the bond angle is going to be less than 109.5 degrees. All right, and so as I said, it's kind of look at all the similarities. If you think about these 4, right, all these 4 have 4 electron groups. All right, and we could see like so, and so they're all derivative of a tetrahedral shape. All right, if you think about the electron geometry, the electron shapes in itself, but the molecular shapes, all depends. So here we have tetrahedral because of the 4 things sticking off it. This is a trigonal pyramidal. Trigonal pyramidal. This last one here, we simply say that if you look at the molecule, right, it's like, oh, it's bent. All right, so this one has more of a bent shape. Okay, but they all stem from a 4 electron group. And so this is kind of a good way to kind of categorize this in your minds. I mean, because yes, this is all have to be memorized, but if you kind of categorize in your mind between, okay, something that has 2 electron groups, 3 electron groups, there's 2 deviations of it, where you have all lone pairs, and then all bonding pairs, and then you have 1 that's a lone pair, and then you have this 4 electron group and its deviations of it, where you have simply in a sense where you have 4 bonding pairs and no lone pairs. You have 3 bonding pairs and 1 lone pair, and then you have 2 bonding pairs and 2 lone pairs. All right. Well, we can never have just 1 bonding pair. I mean, if you have 1 bonding pair and 3 lone pairs, I mean, that is possible, but in that case, it's linear, right? So that's kind of a way to categorize this, and this is Vesper. Okay.